Alright, we're going to cover a little bit of what happens when you stand on a scale and what the scale truly measures, and then we're going to take a look at normal force and ultimately see how normal force can change throughout a certain set of events here. So the first idea is let's take a look at a scale, something that measures your weight. And when you stand on a scale, what ends up happening is that it would normally read your weight. So if you have a, let's say a 50 kilogram person, what would end up happening is that, the scale reads in pounds, and what the scale would read is 110. But you can always get that reading on the scale to change. For example, if there's a counter here and you reach over and you kind of touch the counter and push up a little bit, it might read 90 pounds. If you are standing on the scale, and let's say that there was somebody else who goes and pushes down on you, they apply a downward force on you, the reading on the scale is going to go up. It could say something like 130. Now, the person's true weight is 110 pounds. But the scale reading varies depending upon what's going on. So their true weight is 110 pounds, but sometimes the scale reads less, sometimes the scale reads more. And what the scale is truly reading is not this force acting on you, the force of gravity. It's reading this force, the normal force acting on you. And what ends up happening is that if somebody pushes down on you, your normal force is actually going to increase. And then if someone, let's say, or even if you push up on something else, your normal force is going to decrease. Now we'll look later on as to why that happens, but what I really want to point out is that the reading of the scale is not your weight. What it is, it's the normal force. And sometimes those things happen to be the exact same number. For example, when nothing funny is going on here. So what we're going to do is take a look at elevators, because what ends up happening in an elevator is that you're going to start on a ground level. And let's give you a hypothetical here of you standing on a scale in an elevator, because this is a very interesting problem. And right now the elevator's at rest. You're on the ground level. And what you're going to do is you're going to take it up to the top of the building. So what the elevator has to do is it has to accelerate. Let's give it an acceleration of 1.0 meters per second squared up. Now that's not going to last all that long because your elevator doesn't rapidly accelerate up the entire time you're ascending. What ends up happening is that through a very long period of time, you're in the elevator, and what it's doing is it's moving up at constant velocity, whatever that velocity is. Some of them go faster than others once they're up to speed. So you're going to ascend all the way up, and then at the very top, what you have to do is you have to decelerate in order to stop. So we're going to give it an acceleration of negative 1.0 meters per second squared up here. So you got a lot of things happening in an elevator. You're at rest, you speed up, you coast, and then you slow down. And all of these things will actually involve fluctuations in the normal force that you experience. This is where we get into the idea of apparent weight. Apparent weight is another term for normal force. Basically, when your normal force changes, you're actually going to feel heavier or lighter depending upon the scenario. When I'm in an elevator, I'm getting old now, so once we get started, my knees buckle a little bit right here, and then I don't feel any different up here. And then at the top, what ends up happening is that you may feel a little lighter at the top. In fact, what a lot of people, kids especially, do is at the top of the elevator, they try to jump, because what ends up happening is that the floor, while they're rising with the person, when the person jumps, the floor just stops while they're jumping, and it actually, I would say, results in you going higher than you normally would. So what it does is it actually simulates an environment where you're kind of lighter. At least it kind of simulates it, and you do feel this. So if you're looking at the person here, you can actually only identify two forces acting on the person at each instant in time. That force is the force of gravity. The other force is the normal force. So we can only identify those two forces, and there's nothing else in play here. The person's in contact with the floor, and there's a force of gravity acting on them. So essentially, what's happening is that while this person's moving up, there's only one force that can truly push them up, and that's the normal force. So this is the force that's responsible for them rising in this particular point here. So let's take a look at how this force varies as we go up the elevator. So we'll start at rest, and what we can do is we can say, all right, these are my two forces, the normal force and gravity here. So we'll write the second law out. Sigma F equals ma, and then our two forces here that make up sigma F is the normal force, it's pointed up, gravity's pointed down. So I get this, and keep in mind we'll still have our person here being a mass of 50 kilograms. And so we actually always know what the force of gravity is, right? The force of gravity for this person would be 50 times 9.81. It would be 490.5 newtons. Now that can't change. That's a constant downward force acting on the person. Now when they're at rest, there's no acceleration here. So sigma F is technically equal to 0. And the normal force is unknown, and the gravity is 490.5. So what we get is what we've seen consistently here. The normal force and gravity are equal to each other in this scenario here. But now, once we start to accelerate, that's going to change. So let's take a look at the acceleration portion. And it turns out that the expression that we write is exactly the same, because the normal force is up and gravity is down. But now we have a non-zero value of acceleration. So when I do 50 times 1, the normal force is unknown here, minus 490.5. Just solving for n here will give us 490.5 plus 50. And that is a normal force of 540.5 newtons here. So what we're dealing with here is a person where there are two forces acting on them. The normal force is greater than the force of gravity. So when you look at a picture like this, you can understand why they're accelerating upwards. And in fact, this is what we're getting into, the idea behind apparent weight. For this instant in time, while you're accelerating upwards, you feel heavier. If you guys have ever been on a ride, like an amusement park ride that rises really quickly, it almost feels like you're glued into the seat sometimes. So that's what ends up happening when you accelerate up. Now that's not going to last very long in an elevator. On an amusement park ride it might last longer, because for the elevator, for the majority of it, you just ascend at a constant speed. So keep in mind the acceleration is 0 there again. So when we do the same two forces, what we get is again an acceleration of 0, and so you get a normal force again of just 490.5. You should feel like your true self throughout the majority of this trip, which is at constant velocity. So just because you're moving up doesn't mean you feel heavier. It's when you're accelerating up you feel heavier. And in fact, while you're slowing to a stop, your acceleration is directed downwards. So what ends up happening is that your velocity is up, your acceleration is down, and let's look at the forces in play here. They're still the same two forces. So n is up, f of g is down, but now our a value is negative here. So we write 50, an acceleration of -1. We're going to solve for n here. We know what the force of gravity is, 490.5. So when we do the solving for n here, what we get is a normal force of 440.5 newtons. So when we're looking at this particular person, if I was looking at their force of gravity, it's still the same value here, but now the n is smaller, so I'm not going to draw it as large, and you can see why we have a slight acceleration downwards. F of g is less than n. It's important that you still realize that even though our acceleration is downwards, we continue to move up, kind of like a rising projectile did. All this is doing is slowing us down, and eventually the velocity is going to hit 0 and our elevator will come to rest permanently there. But let's note this value here, 440.5. We feel lighter in this scenario. So this actually simulates an environment where you actually feel lighter than you do. You could technically actually bench press more for that short instant in time that this happens. And like I said, everyone likes to jump here because what it does is this floor stops while you continue to go upwards, and you've already built up a little bit of speed from the floor, and it kind of it exacerbates the distance between the floor and yourself here. So it's a very interesting scenario, to say the least. We will go over how about descending in an elevator next, and then a very unique scenario in another video.